Lecture 7, Sockets. So this is another form of inter-process communication. Use of sockets is actually quite large, so it's going to be spread across more than one video and more than one topic in the lecture notes. But it is a very important mechanism for inter-process communication. What makes network communication really quite different from the other kinds that we're going to talk about, which include the message queue, which we already covered, pipes, shared memory, that sort of thing, is that it allows communication between processes that are not running on the same machine. And while you can, of course, use sockets for communication between two processes on the same machine, it is your only choice, really, if you are interested in communication with different machines. And ultimately, that is where things are going to go in whatever program you're working on. It is likely that it is going to have to communicate with different machines over the network. But of course, you could use sockets if, say, client and server are both running on the same machine. That's also allowed, and you might actually choose that in the beginning because it allows you to later move the client and the server to separate machines if that's your wish. So we'll have to talk ever so briefly about the internet in general. And if you listen to the people who make laws about the internet is merely a series of tubes. This being a very famous quotation from the former U.S. Senator Ted Stevens. He was senator from Alaska, I believe. And it goes to show that sometimes the people who make laws about these things don't have a very good understanding of the topics that they are making laws about. Now, ideally, they have input from experts about what is supposed to happen, but I guess what I'm saying is you should vote, even if you don't think voting is important. It actually is, because if you don't vote, then people who don't know will vote, and you end up with the internet as a series of tubes, as not just being, haha, funny, let's make fun of that ridiculous statement, but also this is actual policy as implemented by a government or regulatory agency. So the internet is more than just a series of tubes, as you should know. Now, if two processes are not on the same machine, we're going to have to use it. The internet is frequently portrayed as just a mysterious cloud or blob, and that's fine. There are obviously implementation details for how that is going to work, and what the internals of this are, and how does the data get from here to there, and what are the various layers of the internet. There is a whole course that covers network communication, should you choose to take it, and how they function, how they behave, and what the various layers are. For our purposes, we are just users of the network. We will assume that the network exists, and we will use it from the application level, and we're not interested in trying to peel it back too far and figure out what is going on in its implementation. And the socket API is used to describe how network communication is going to work. And this is a standard dating back many, many years, and the concept is about how to establish a communication channel. There are two ways we can communicate. There are datagrams and there are connection streams. Now, the socket analogy does to a certain extent resemble an electrical socket. That, I have a laptop and I want to charge my laptop. Well, I get the power adapter out and I plug the cable into the wall socket, as depicted on the slide. And when I do that, I have established a connection. And that connection is then how data is going to be transferred in a network communication scenario, but it's also how power is transferred in this analogy. And for as long as my network adapter remains connected, then the power grid can provide power to my laptop, and when I'm done, I can disconnect, and that will be the end of it. The connection stream is to some extent like a telephone call. And this is that, you establish a connection by dial a number, and both parties have to be available, not on the phone already or away from their phone or something like that. And if they answer the call, then a line of communication is established, and that allows for the exchange of data. At some point, one side or the other will hang up, and that ends the call. Now, the telephone network has to do quite a bit to get your data from one end to the other in a timely manner, but that's not really your concern very much when you want to make the phone call. You just specify the number you want to dial or the name that you want to dial in your contacts list, and you make the call, and whatever happens in the background happens. If the other person answers, then connection is established and you can talk. Datagram is not like that. Datagram is more like texting or sending a letter in the mail, snail mail. You can mail out letters, but letters can actually be delivered in any order. They might get lost along the way, and they are unidirectional. The recipient of a letter can write one back if they desire, but they might not want to. And there's no connection to be established. It is just simple message delivery. So there is a big difference between the stream approach and the datagram approach. We will focus much more on the stream approach than we would on the datagram approach, but that's just your option. You could choose whether a stream or a datagram makes more sense. Now, much like everything else in Unix, a socket is a file, and it's treated as such when we want to work with it. So to create a socket, we need to have the socket.h header, and then we can create a socket with the system call socket, which takes 3 parameters, domain, type, and protocol, and it returns an integer. So the domain value tells you what kind of address we are interested in. It defines the address format, and it's how we choose between IPv4 and IPv6 or other things if there's a different protocol that we are interested in. For the purpose of this course, we're going to use IPv4, and the constant for that is AF-INET, which means Address Family Internet. Why IPv4? Well, IPv6, grand dream though it is, hasn't exactly had a ton of success out in the world. Why? Well, IPv6 addresses are fairly hard to read, and there are a number of programs and protocols that don't support it natively, and you have to have like weird hacks or patches introduced to actually make that happen. Moreover, the designers of IPv6, I think, failed to realize that one of the things about IPv4 is that it is actually kind of human comprehensible. If I ask you, you can probably tell me some IPv4 addresses. You might say, oh, I know that the IP address for my router is 192.168.0.1, and you would be correct. And assuming you have a router that chooses that as its IP address, you could have a different number in there. There are 4 segments. Each segment is a value between 0 and 255. And some of them are obviously reserved for various purposes. And the 192.168 is intended for your internal personal network. Now, the thing about that IPv4 address is it's quite memorable, that you could remember this and it's not too complicated. IPv6 addresses are longer and complicated, and things are optional, so you could have a colon followed by another colon, which means just skip the segment, it's empty. And I'm willing to guess that you probably don't know any IPv6 addresses. When I asked students who took this course with me in the fall term of 2019, nobody could tell me any meaningful IPv6 address, and this evidently hinders the acceptance of it. It's harder to use. Why do people want to use it? But hey, this digression on why IPv6 is not super successful can wait for some other time. For now, we need to get back on track with how to actually use the socket. Now, for the purpose of this course, as I say, we will use IPv4, and the constant for that is AF-INET, and that's what we should always assume will be provided for the domain type in a call to socket. Then for type, we choose whether we want a datagram or a stream. SOC-dgram is for datagram and SOC-stream is for stream. That is straightforward. And SOC-stream is bidirectional byte stream. We'll come to that when we talk about sending and receiving, but that is how the connection is configured. Protocol is our choice for how data is transported. And if we choose a stream, the default is TCP/IP. Without going into too much detail about what TCP/IP is, Transmission Control Protocol over Internet Protocol, it's the way that a lot of data is transported over the Internet. This is a mostly reliable method of transport that makes sure your data gets where it needs to go with all of the pieces arriving in the correct order. With TCP, you might send out, let's say, 20 packets of data. If they arrive out of order, the recipient is able to put them in the correct order because the packets tell them this is the correct order and this is how we organize them. If the recipient makes a determination that one of the packets is missing, it says, oh, I did not receive packet number 8, it will request from the sender again saying, could you please resend packet 8? I didn't get it. Or if packet 12 was corrupt, it will say, sorry, packet 12 was corrupt, could you resend that, please? And that makes TCP a mostly reliable method of transport. Obviously, if the internet goes down, the cable line got cut by a construction crew who cut the wrong thing, that means that the message won't arrive, or only part of the message will arrive. There are some things that you can't solve at the TCP level. If you choose datagram, 0 for the default gives you UDP, which is not a reliable method of communication. Data packets might get there or they might not. They're just sent, and if they're received, and if they're not, they're not. You might think that UDP is useless, but that's not really true. UDP is used quite frequently in scenarios like you're watching a streaming video. If you are watching a streaming video and some data gets lost, that's okay. We'll just carry on. It's a live broadcast. We'll just carry on. That's less harmful to the user experience than pausing it and buffering every time a packet gets lost to make sure that we didn't miss a single pixel, we didn't miss a single frame. And so UDP is sometimes used in that situation. However, for what we want to do today and what we want to talk about in this course, we're interested in stream connections with the domain IPv4, and we want TCP/IP. The return type of socket call is an integer, and that is a file descriptor. And just like that, we have a socket that is open, and we have created it. There's obviously more steps to do before we're ready to communicate over the internet, and that's fine. We should also remember that a socket needs to be closed when we're finished with it. And for that, the system call is close just the same as it was with a file. And you may have noticed that things are maybe not entirely symmetrical in that open is used to open a file and socket is used to open a socket, but close closes them all. That's because when we want to open a thing, we have to say what kind of thing we want to open. When we want to close something, we already know what type it is. The system already knows what it is, so closing it and how to actually do that is easy enough to figure out. Okay, now consider the title of this slide. Check the boot of the car for your jumper. In an interactive session, I would ask anybody if they know what it means. Again, in the fall term, somebody thought it had something to do with jumper cables, for starting your car if the battery is dead. It is a British English phrase that means, in Canadian or American English, check the trunk of your car for your sweater. So, as you can imagine, speaking the same dialect is important, not just in everyday human communication, but also in how we interact over the network. And if we consider a 4-byte integer, there are two possible organizations that define how the integer is stored in memory. And they are big endian and little endian. And in big endian, the most significant bits go up at the beginning, and in a little endian, it is the reverse. Now, whether your system is little endian or big endian depends on the CPU architecture. And for x86, for example, it is a little endian architecture. PowerPC is a big endian architecture. You might actually think that Little Endian makes no sense whatsoever. That is because you are a human reading a language left to right, in a case where we put lower memory addresses on the left and higher ones on the right, just sort of by convention. The computer does not care about that sort of convention, and it is all the same to the computer whether it is Little Endian or Big Endian architecture, and the only thing that matters is that we agree on what format is sent over the network. Because some architectures are Little Endian and some are Big Endian, it's not okay to make an assumption about what the architecture on the other side is. And for that reason, the network protocol says you have to use the Big Endian format, and that means it is necessary to translate values into a Big Endian format. And you should use the conversion functions that we're going to see momentarily pretty much always, even if on your system they might do nothing, just because by default your system is Big Endian. It's a good habit to make use of these as appropriate. And included in the header arpa/inet.h, there are some functions that help us out. And using them makes your code portable and ensures that the sender and the receiver agree on the content of the message. So there are 4 functions, and 2 of them are for converting from network format to host format, and the other 2 are the reverse direction, and 2 of them are for 32-bit types, and the other 2 are for 16-bit types. So the first one on the list, H2NL, that's from host to network format, that reason H to N, and L for long, in this case 32 bits. H2NS, it would be host to network format short, so for 16 bits, and for the network to host, N2HL and N2HS variants exist. And yeah, they come in these 32 and 16-bit types. Now, the return types and the arguments don't look like integers or even just your regular unsigned integers, do they? Well, no. Sometimes we have to be quite specific about the size of the integer that we are expecting. As you can imagine, these routines don't work correctly if the size of the integer is not the same as the size that you expect. And this means that when you are communicating via the network, you might need to explicitly choose, yes, I want to use 32-bit integer types, and therefore not just rely on whatever int happens to be implemented as on your system. This is one of those things where, yeah, when other computers get involved, it starts to get more complicated because we don't agree necessarily on what the size of an int is, and therefore we have to be explicit about what the size of an int is to make sure that everybody agrees. The more complicated the system gets, the more strange and corner cases you have to account for, including now things like, well, what if ints aren't always the same size, and what if the system is Big Endian versus Little Endian? All of which you can mostly ignore when you are just working on one machine without sending things over the network. Keeping in mind that we need to communicate using the right format, when we want to call somebody, we have to put in their phone number. Well, whether we store that in the contacts list or if we're just dialing a number directly, that's got an address of some sort associated with it. In this case, it is a phone number, 10 digits in North America. If we want someone to call us, we need a phone number, and we need to be ready to receive calls. And both of those things are analogous to your structure for this, which is an internet address. And the structure for an address is struct sockaddr in, and it has 3 fields that are worth talking about. There is the address family, there is a port, and then there is another struct inside of this, the struct in addr, which is the IPv4 address if we've chosen IPv4. So here's the sample initialization of this. If we want to create it, we will just stack allocate here, struct sock adder in ADDR, and we'll set the family to be AF INET, which, as we've previously discussed, is IPv4. And we will set the port to be, and then we're going to use our host to network conversion format here for 2520, and then we have the last one where we choose the address of host to network long, so 32-bit, of a constant internet address any. Okay. IPv4, we know how those work. They take a format like 192.168.0.1, and each of the four groupings is a number between 0 and 255, and that's how you connect to your router. When you go to, in your web browser, uwaterloo.ca, there is, done for you behind the scenes, a translation that transforms this into an IP address, which would be something like 129.97.208.23. The computer uses the number. The name is nice for human. You do like uwaterloo.ca because that's a lot easier to remember, and it's much more painful to memorize IP addresses, and they're harder to remember, and they sometimes change. So you have to look them up. Web addresses change somewhat less often. Here, instead of actually specifying any sort of address, we chose this constant internet address any. This says choose the current IP address of our computer. You could actually have several values if you have more than one network connection. If your computer has an Ethernet network port and it has Wi-Fi and both of those are connected, you could actually have more than one. But we don't want any specific address. We'll just take any address that our computer currently has. And what about port? Well, if you want to think about the address of the computer being like a street address, then imagine that your computer is kind of an apartment building, and the port number is which apartment the connection is made with. So different services, these are processes, will communicate using different ports, and no two processes can be using the same port at the same time. By convention, ports that are below 1024 are reserved for system services. These ports that are below 1024 require a root or superuser access to make use of, and for our purposes, we are going to always use ports that are above 1024, just because those are the ones that we are allowed to have access to. And this allows your computer to have many open connections concurrently. You can have different ports that are communicating with different remote servers, and they don't interfere with one another. We're not limited in that regard, as long as no two ports are trying to be used by more than one process at a time. So when you log into a server with SSH, for example, the default port on the remote side for that is 22. This is a, in quotation marks, well-known port, in that everybody agrees up front that this is the standard port for this service. And by default, when the server starts up the SSH daemon, it knows to listen for connections on port 22, and by default, when you specify an address like SSH user ID at ECU Ubuntu, then by default we're going to connect to port 22, and everybody knows that this is the default and that's what happens. And for lots of standard system services like SSH, like FTP, and so on, there are well-known ports where you can always expect to find the remote server. For a web browser, it's usually connecting at port 80. Those are usually reserved and only make sense because they're below 1024 in the list, but it is unexpected for a service that's not SSH to be running on port 22. That's not to say that you can't. There's no law. The internet police are not going to come arrest you if you do, but it might be unexpected. And you can, of course, run an SSH server on a different port number. You would just have to specify in the command line, oh, please connect to port of 4022, if that's where you've decided it's going to listen, and that would be okay as well. And of course, in the example that we are doing, we are using port 2520 because this is ECE 252, but of course we can't use port 252 because it is reserved, so I've just tacked a 0 on the end to make it such that it is no longer in the reserve range and does not conflict with any well-known service that is likely to run on that port. There are incidentally some websites where you can look up what services normally run on which ports. Again, it's not the law, but if you weren't sure, and it is a fairly standard service, it is a way you can look it up. You might also have experienced, I don't know if this has happened to any of you, but it happened to me one time, where as an interview question I was asked about what ports, what certain services run on, what's port 21 correspond to. Why that is important as an interview question, I don't know, but nevertheless, it is something that people asked me one time, and I'm still wondering about it to this day. But the next thing that we are going to do is learn how to look up an address. You see, in real life, it is unlikely that we are going to actually use an IP address, except in certain circumstances. If you want to contact your router, you might choose that. In this course, in assignments, you might choose a specific IP address that has been specified, and that would suffice. So you can just be like Arnold here, looking up the address as you need. That is more common because usually you as a human, you want to type SSH username at eclinux.uwaterloo.ca, and you don't want to manually look that up. You can. There is a command line tool for this, and it's called NSLookup, and you just specify that, but why? You can get the computer to do this for you, and that would be better. So many of the examples that you will find on the internet use a older method for doing this, and they use a function called getHostByName. That is officially deprecated, and it has been replaced with a new function, and we're going to learn the new one. You might still see getHostByName in the wild. You might encounter it in some sample code. You might see it in code that you actually work on in industry, but we're going to learn about the new method instead because it is more up to date. And the new one is called getAddressInfo. It takes 4 parameters, and we can specify what we're looking for. So first parameter is the node. This is the host name or the IP address represented as a string. So you would put www.example.com as the address that you wanted to provide. That would work. You could also specify as a string the IP address 192.168.0.1. That would also be fine, again, as an explicit string. Then we have the service, and the service is either a protocol or a port number. So certain protocols, as I mentioned, are associated already with port numbers automatically. HTTP is, for example, what you use for your web browser, and it's associated with port 80. You can use the name for it, but you could also explicitly put a port number. If we wanted to specify our own custom service, something like in this course, then we won't be able to use the service name. We will have to use the port number that we have explicitly chosen. And then there is a pointer construct address info hints. The hints can be used to optionally restrict the kind of connection that you want, and you can use the hints to say you're only interested in a connection that is of type IPv4 with TCP stream sockets, and let the function getAddressInfo fill in the rest of the details. And then there is the last parameter, struct addressinfo $res. This is a pointer to a pointer, and res is pointing to the structure that will be updated when the function is done. This sort of violates the convention that I introduced in the RC Toolkit lecture about how it is usually the case that it's the first parameter that is updated. I said that wasn't a hard rule, and this is an example of where that's not the case. In this case, it is the last parameter that is updated and is updated with the result. The function does have a return value of type int, and it is used to indicate 0 equals success. So let's actually try to use that, shall we? Okay. We declare 2 struct address info types. One is a regular stack allocated one, another is a pointer. And we will then memset the hints. We're going to fill it entirely with zeros to make sure that the struct is empty. For our hints, we want the family to be IPv4, so constant AF INET. We want the socket type to be stream, and we will use a constant AI passive for the AI flag, saying we don't care what the IP is, we want that to be filled in for us. Okay, and then to actually complete this, we call getAddressInfo with www.example.com, port 2520. We provide a pointer to the hints, and we provide the address of the pointer for server info. This is where the double star makes sense. We're providing the address of a pointer. If I go back here, double star means pointer to a pointer, so providing the address of a pointer is correct. That pointer will be updated to point to the result. So server info will point to the result if getAddressInfo succeeds. If the result is not 0, something went wrong, and in the example code here, we just return -1 from this function. And then, if it did succeed, we go on, and we can get the address information by unpacking the result a little bit. And what we need, the struct sockAddr_in pointer to it is found in server info with the field AI address. So we actually get a linked list of results back because www.example.com could resolve to more than one IP. That's the case if you tried to look up, say, the IP address for Google. You will end up potentially with multiple results. For other services, you might only get one result. Either way, we're just interested in the first result, so that's what we'll take from this list, and then we can do something useful with it. And finally, there is a free address info call, which is the corresponding version of getAddressInfo. This is one of those functions, getAddressInfo is, that returns memory that it has allocated to fulfill your request, and that means you, as the caller, are responsible for deallocating this when you're finished with it. So if you are interested in getting the information out of getAddressInfo, we provide it with the information that we want to get. We provide it with some hints. It finds a result, if there is any result to be found, and returns it to us. And that returned result is newly allocated memory that we are responsible for disposing of when we're done. If you're interested in getting the structure for your local computer, we can manually initialize the struct sockAddressIn as we did earlier. I'll just scroll back a bit so you can see the example of that where we allocated it as shown here, where you just stack allocated it and you manually specified AF INET and the port and the INET address, any constant. You don't have to do that. You can also use getAddressInfo to find our own information. You just provide null as the node parameter, so as the first argument, instead of providing here getAddressInfo with a URL or with a IP address, you just provide null, and then that looks at our own computer and decides what is the address for that. So it's also possible to use null for the hints if you're willing to accept the defaults, that is, whatever getAddressInfo comes up with. That might not be what you want, though, because it might come up with an IPv6 address, if one exists, and you can't make use of that for an IPv4 connection. So it is usually wise to use the hints to restrict the kind of answer that you are asking for. And as I've previously mentioned, it is required to use free address info to deallocate the results when we are finished with them. Okay. If you find a fork in the road, keep it. Up until now, everything that we have learned about applies to both the client and the server side. getAddressInfo can be used for finding our own information or for finding information about a remote server. And you have to open a socket on both sides. That part is the same, and use free address-info with whatever was allocated by getAddressInfo. And both sides have to convert from host to network format and network to host format to make sure that everything is going as expected. Now the paths diverge. There is a different workflow if you are the client connecting to a remote server than there is if you are the server and you are expecting incoming connections. This will make a little more sense as we actually get through some examples, but it is important to note that at this point we have to split our path, and we're going to choose the client first because it's the easier workflow, and it is a little simpler to understand, and we should have a good grasp of how it works before we try to go on to the server workflow, which is more complicated and involves more steps. So the client workflow is pretty simple. We have created a socket, we have an address, whether it's manually created or we use getAddressInfo, and then we would actually like to connect to the remote server. And so the client's function for this is called connect. And connect is also simple to use. It takes 3 parameters. It takes the first one, sockfd, the file descriptor, the int we got back as the return value from the call to socket. Then the address structure, so the one that we got from getAddressInfo that we have looked up, www.example.com, port 2520, that address, and then a length, which is the size of the address structure. And there's 2 ways to specify that. One is you can use the size of function, or size of operator, really, the way that you would say size of int to have the compiler work out for you what is the size of an address. However, the address itself has a field AI address length, which you can use if you want to use that instead of size of. And when you see the example, this will perhaps become clearer. So we have a client example here, just a snippet, not the entire code, where we declare hints, we declare a pointer for the result, we declare a socket file descriptor. We will memset hints to be all zeros. We will then say we're interested in AF INET, IPv4, and a socket stream connection. And then we will use getAddressInfo on www.uwaterloo.ca, port 80, with the provided hints, updating the res pointer accordingly. Obviously, we should check the return value of getAddressInfo, but to try to make it all fit on the slide, I've cut that out here. And then we can create our socket. And we create the socket actually after we've done the address lookup because it allows us to reuse some properties from the result without having to manually specify all of the details. Instead of having to specify again, we want the socket to be AF INET as the domain, and we have to specify as well any other of the fields, the type, and the protocol. We can actually just unpack those from the result by using the results address family, socket type, and protocol. Now, everything should be exactly as we expect. We should expect it to be AF INET, so IPv4. It should be a stream type, because we said we want it to be a stream type. And the protocol should be TCP/IP, because that is the default for this type of connection. However, why enter these things again when we can just unpack them from the result? And then we are ready to connect. And connect takes the socket file descriptor, so the return value of socket, the address, and the address length. Again, both of which are properties inside the result. And that's easier, I suppose, than using size of, because since it's provided for us, we know the actual size, and there's kind of no problem there, instead of having to try to figure out what is the return type from res. Don't have to sweat it. The return value of connect determines whether we have successfully connected or not. 0 indicates success, anything else indicates an error. If you take a quick look at the man page for connect, it will tell you about many of the different possible values, what happens if something goes wrong. Some of the possible errors you might encounter are something like the file descriptor provided by socket is invalid. For some reason, opening it failed. You might also see connection refused, connect failed because the remote client declined to open a connection. You can end up with lots of different error codes. It is worth looking at the man pages to actually figure out what's going on. Connect is another one of those functions where -1 is returned in the case of an error, and the error number variable errno is set to tell you what went wrong if something did in fact go wrong. And it's always worth looking at to figure out what's going on. Printing that code to the console maybe isn't super helpful, but if you check the status variable and you see it says E timed out, you know what went wrong. That's much more helpful. So you do have to check against the constants in the implementation that you have. So the client-side workflow is pretty simple. Once we have established where we want to go, we say connect, and if there is a server on the remote side that is ready and willing to accept our incoming connection, then we do. There is a connection is established, and we're ready to go. We can then begin to communicate. We haven't actually communicated yet. All we have done is establish a connection. So we called the other person has picked up. Nobody has said anything yet, but we are ready to communicate. The server workflow is significantly more complicated. The server workflow has 3 steps. The overview of those steps are bind, listen, and accept. The bind step is how we choose what port we are going to have clients connect to. The listen step is the part where we wait for incoming connections from a client. And the last step is accept, just like in the stages of grief, I guess. And that is establish the connection so that we can start talking. So if you wanted an analogy of this sort of thing, bind is we are assigned a phone number. You go to your cell phone provider and you get a SIM card from them, and you are assigned a phone number, 519-555-0001. That number is then assigned to you, and it can't be assigned to anybody else. And that is like bind. Listen is when you turn your phone on. So your phone is on, you have your SIM card installed. If people call that number, then it will make your phone ring. And listening means that we are ready for people to call us. Maybe nobody has called us yet, but we are ready for it. And accept is when somebody is actually calling you, you press the green icon or swipe or whatever action you take to answer the phone call. That's accept. That establishes the connection. So bind is how we set up. This is where we are going to listen. Listen is we are ready for connections to come in from a client. And accept is someone is trying to connect with us. We are now ready to open communication with them. And we'll look at all 3 steps. Conveniently, all of the functions that we need are called bind, listen, and accept, so there's no unexpected verbiage there. And operators are standing by. All right. Bind associates a socket that we have created with whatever port we have chosen to use. The SSH daemon does this. When it's available for a connection, it's because it binds itself to port 22 using bind. If we are interested in, on the server side, reserving a port on our own local machine, we declare a socket. We can just declare it with IPv4 socket stream 0, meaning TCP IP for the defaults, and then we can set up our address, just as we did in the first example of how to create an address, and we will say IPv4, port 2520, converted to network format, and the address, any IP address for our computer, also converted to network format. And then we have bind, and bind says we're going to associate this socket with the address as provided. And the address, again, means whatever IP is the one for our computer and the port that we have specified. You'll notice that bind doesn't happen on the client side. This is because we don't care on the client side what the outgoing port number is. That doesn't matter. On the server side, it does matter because the SSH daemon is reachable on port 22 because it has chosen to bind to port 22. And if it's not there, we don't know where it is and we'll have trouble finding it. if it's on the client side, the outgoing port doesn't matter all that much. Just in the same way that if you want to make a phone call, if you're calling the university switchboard, let's say, so you call university 519-888-4567, what your outgoing number isn't actually that important. As long as you have a number where you can make the call, then that's fine. You will still be able to establish the call. However, if the university wants to receive your call, it has to have that number that you know or can find. Otherwise, it won't be able to receive that call. You will be calling random numbers hoping you find the university. That doesn't make sense either. Okay. Listen. In this step, we wait for incoming connections, and it is very simple. It is much easier than any of the other steps that we have covered thus far in network communication. And listen takes exactly 2 parameters. We listen on a socket that has been bound using bind, and we allow a backlog of up to whatever the second parameter number of connections is. You can usually put in a value of 10 or 20 or something like that. You cannot put a huge number. If you ask for a backlog of 10,000, the system will just cap it at whatever it considers a reasonable amount. But this is a queue. So if there are more connections coming in than we can handle right this very moment, that's okay. We will just put them in the queue. If the queue gets full, the server rejects additional requests. Fair enough. If there's too many requests, we can't possibly answer them all. So on the server side, we've finished our setup. We reserve the port that we want with our socket. We have started listening. We're ready to receive incoming connections. And then when we actually observe an incoming connection, we have to accept. So the first parameter is the socket that we are listening to, and the second and third parameters in the call to accept are information about the client. So you would allocate an address structure and know its length, and you can allocate them and pass them in, and they'll be updated by the call to accept. If you don't care about the identity of the client, then you can just provide null for the second and third parameters. Not caring about the identity of the client doesn't mean you're unable to communicate with the client. It just means you don't have a structure locally where you know their IP address and all that stuff. You might want that in a real scenario where you might be interested in logging. Where did this request come from? Or in case you need to keep this information for some reason. But in a simple scenario, you could usually just provide null, and it doesn't matter because your connection will be open and you will still be able to communicate. The most important thing I want you to remember about accept is accept returns a new socket. The return value is a new file descriptor which describes a new socket, and communication with the client takes place using the new socket and not the original one. This is not what happens on the client. On the client creates a socket, it calls connect, and all communication happens using that one socket that we have created. On the server side, that's not the case. On the server side, when accept runs, it returns a value, and that value is a new socket, and the new socket is where communication happens. The reason for that is that communication with the client takes place using the new socket, so the old socket, the original one, is still available to accept more incoming connections. And if you do not remember this, it will not work as expected when you write your assignments that use this behavior, and you will have problems. So you need to, again, take away from this that the new socket is returned by accept, and that is the one where communication actually takes place. Now, accept is a blocking call. So if accept is invoked and there are no requests in the queue, the server is blocked until a request arrives. We're simply waiting for an incoming connection. So here we're going to put all the pieces together. I've skipped, unfortunately, some of the error checking to make things a little bit more compact to make it all fit on the slide, but that's okay. So we'll declare here a struct for the client address We'll assume in this example that we care about it, just so you can see how that works. And the size is computed for us by size of socket address in. We have a new socket file descriptor. So as the server, we will create our socket on which we're going to receive incoming connections, IPv4, socket stream, default TCP IP. And then we will specify our server address, AF-INET, port 2520, address any. That part is not new. And we also saw how to do bind before, and that hasn't changed either. Bind on the socket FD that we've created with the address that we have just created above and its size. New part is we're going to listen, and listen takes place on the socket that we called bind on, and in this case I've chosen a queue of size 5, and then we will call accept as the next step. And the new socket file descriptor here is the return value of accept. There is a typing error here in the slide. It should say socket FD. There's an E missing. I will probably correct that in GitHub after this. And then we have the socket address for the client address provided, and pointer to it with ampersand, address of, and the client address size. So accept waits for an incoming connection on socket FD. When that happens, it updates the client address and the client address size with whoever the remote client is. And the new socket file descriptor is assigned the value, and all communication happens via that new socket file descriptor. That part is the do something useful comment here, so we will send some data, receive some data, whatever we need to do. When we're finished talking to that specific client, we can just close its socket, and when we are done listening to everything, when we're not interested in receiving any more incoming connections, then you close the original socket file descriptor, and that undoes all the listen and bind and all that stuff. So there's no unbind and there's no unlisten system calls because they're not needed. If we close the socket, that's how we indicate that we're done. We probably want to accept in a loop. Unless communication is a one-time thing, it's more likely that we call accept in some sort of loop where we are accepting incoming connections, doing something useful with each, and then going on to the next one. You know, your typical server is not a one-and-done kind of operation. You are listening for many incoming requests, you handle each request, and then you go on to the next. If you are interested in a more compact version because we disregard the client address, then that is shown here, in which we don't declare the client stuff. And the only major difference is, of course, we don't declare those, and accept is called with null as the final two parameters. And the only thing that we actually have to specify is accept. And again, because this is copied and modified from the previous example, the typing error that's in there in the previous example shows up here too, and this should actually be corrected. Okay, after all of that, connection established. We're finally ready for both the client and the server to communicate. Again, the client is using the original file descriptor and the server using a new one. There is a lot of setup when we learn about sockets for the first time. We have to cover a lot of ground about, well, what is the workflow for the client and what is the workflow for the server, and how all of those things actually happen. It is likely, if you write a program that does a lot of work with sockets, that some of the lines of boilerplate will be put into functions that you can invoke with relatively few parameters. You might, on the client side, write some function like int connect to, where you just specify a host and a port, and then you don't have to go through the whole thing about declaring the struct every single time and calling get address info and checking the results and all of that stuff. You can abstract that away into a function, therefore reduce the amount of repetition that you actually need. This kind of function does initialization, gets the address info, calls connect, checks for errors, returns the file descriptor for writing, maybe -1 if something went wrong. That's fine, but we have to learn how the magic works before we can use it. And if you can believe it, after all of this, after we've covered all of these steps and all of these functions and everything, the client and the server still haven't exchanged any data. All we've managed to do is establish a connection. We showed how to establish it on the client side, and we showed how to establish it on the server side, but no data has yet been exchanged. And it's as if the phone calls have started, so client calls the server. We've done all the work of telling people our phone number and of getting our SIM card and all of that, and the client has called the server, but no talking has happened. So our next topic is going to examine that in some more detail about how do we actually exchange data between the client and the server when we are ready, when the connection has been established. However, this topic has gone on quite a long time already, so I will leave that to the next video. And see you there.